Right, so today we'll talk about problems with synchronization, in particular deadlock in the context of operating systems, and perhaps some other synchronization issues. So you've probably, some of you have heard of this problem of deadlock, and perhaps even the dining philosopher's problem. Who's heard of the dining philosopher's problem? Couple. All right. Well, you're going to have to hear it again. Let's, where did I put it? Ah, here we are. Okay, so here's the idea. We have a bunch of philosophers. They're out to dinner. And philosophers, being philosophers, they're very strict about their rules and how one should dine. And they're eating rice. There should be a rice bowl in the middle here. Put a rice bowl. They're eating from a rice bowl in the middle. Ah, come on. Rice. And as you all know, when you eat rice, you have to use sticks. Use these Chinese eating sticks. It's very hard to eat rice with only the one stick. So the general idea here is you take two sticks, you eat until you're full, and you put the sticks down. So unfortunately, what happens if you follow just this rule, and let's make it a little bit more formal. You take your stick on the left, and then you take your stick on the right, and then you eat. And then when you're done, you put both sticks down where they used to be. So if you follow that rule, unfortunately, all these philosophers will die of starvation. What will happen, at least, if they're perfectly synchronized, and let's start with that, then for sure, they will all pick up the stick on the left. So this guy gets that one, this one gets this one, and so on, and this one gets that one, which is on the left of him. And so now everyone has one stick, but there are no sticks left on the table, and now they wait until the other stick becomes available. And that will never happen. So this actually happens even if you do it more randomly. Like you start eating at random when you feel hungry. And after a while, you will end up in this situation where everyone is holding a left stick. And after that, the things don't change anymore. So that's what happens in threads a lot when you start having more than one lock. In this case, I suppose we can think of the sticks as locks, right? And so if there was, let's say there was only a pair of sticks lying in the middle instead, and you take the pair at once, but it's only the one pair, then there's no way you can get a deadlock. Now, one philosopher gets to eat, he'll be done and then put it down, so that doesn't cause any real problem. But generally, we want more than one lock, because with just the one lock, only one philosopher can eat at a time. So we try to add more locks to make the system more efficient, but then you end up with deadlock instead sometimes. So let's think about what makes this, what are the criteria that make deadlock possible in this system? What is wrong with the setup that makes it even possible that these guys could starve? So I think we have to start with mutual exclusion. One philosopher can uses stick at a time. Only one. Wow, it's really hard to do this in this drawing program. All right. Okay, there's the first one. If somehow magically two of us could use a stick at the same time, then for sure it'd be fine. We could just share each of the two sticks and we'll be able to eat. That doesn't work here. It doesn't really work in locking either. Right? The whole point of the locking being only one can enter the critical section. Otherwise, we have other problems, race conditions in particular. So that one we can't really do much about. Or actually, I take that back. One way to avoid deadlock is to not use locks. Right? You can write lock-free data structures, and in which case you will not have deadlock. In fact, that's the main reason people implement lock-free data structures, is because then you don't have to worry about these things. They're usually not as fast. At least if the system is heavily contended, usually a lock-free data structure will go slower, but there's some guarantee of progress, and that's really attractive, especially in sort of life-critical situations and guidance systems and that sort of thing. But maybe also if you're trying to play a movie at a certain frame rate. Okay, next up, it's called hold and wait. So if you need a second lock, you hold on to the one that you had. Right? So we don't release our stick before we've eaten any stick. Right? So what's the equivalent in locking? Right? With sticks, I guess it sort of makes sense. In locking, the idea is you have nested locking. So you acquire lock A, you do some work on the shared data structure, and then inside of the critical section of lock A, you lock B as well. And now the problem becomes B is not available. I will hold on to A forever, or until B becomes available, just like with the sticks here. All right. With just these two, we're not going to have any deadlocks. However, there's no preemption. Meaning, I can't just take a stick from someone. Right? That would be a solution too. In fact, if just one of these philosophers are a little bit more aggressive than the others, then no one's going to die. Right? He'll just take the initiative, grab a stick, eat, and now everyone's fine. Right? But they're all kind of peaceful. So there's no preemption. If you're holding a lock, no one can take the lock away from you. In a normal software system, it'd be really complicated to support preemption. The problem is you're halfway into a critical section. You've made some critical changes, but you haven't finished. So it could be there's dangling pointers in your data structure that you will fix after you're done with this lock acquisition. You're going to fix that part, but you haven't yet. And now someone just takes the lock away, so you're not okay. And what does it mean to take a lock away? I mean, where would we continue executing from? I should write some. Let's have an example to think about this. So we have some function. It goes lock A, do some critical section work, lock B, more critical section work, unlock A and B. So, okay, maybe let's try this. We go balance minus equals transfer amount. So we deduct some amount from let's call it A balance here. And then we add some money to the B balance. And then we unlock both. So why do we have to acquire locks at all, by the way? This is a banking sort of transaction here, right? transferring money from someone's account to someone else's account. Why do I need these locks?
Some other thread would come in and modify the amount, and the end result would differ if two threads update the amount at the same time.
Right. So it's the same as with the I++. Well, there's two things, I suppose. Here, just like with the I++ example, you might be able to subtract an amount twice, but the result is only one subtraction. Right? So money just appears out of nowhere. That would be bad. Or money just disappears out of nowhere. Here you add the amount twice, but you only get one. In the end, the balance only goes up by one amount. Usually you would also have something like this. If a balance is greater than amount, all right, else return. You may have seen this go-to stuff in places. It's actually often necessary when you start having locking. Right, so this would be a common scenario. See if there's enough money in there. So even if this increment and decrement was atomic, you would still need to have a lock to make sure that the balance is available before you deduct it. Otherwise, you might end up with a negative balance, and that's usually not good. Okay. Actually, I should probably clean this up a little further. Right. So this is actually kind of an important point here. See how I did return? I go to exit. I have to unlock A, because otherwise we have a deadlock right away. Now I can have a deadlock with just one thread. The lock never gets unlocked, so next time the thread tries to acquire it, well, it's over. There's no way to get it again. You will probably see lots of people complaining about goto being a bad thing. You should not have goto in your programs. Shows up every now and then, but they probably don't use locks a whole lot, at least not in C. You have to have goto in this situation, or you'd have crazy number of copies of all your exit code. In this case, the exit code is simple, but there could very well be other cleanup you need to do at the end. So if you have gotos and they just go down the function, generally that's fine. That's perfectly good design. The problem is if you have a goto from here that goes up, now you have an implicit loop and things start getting really hairy. In other languages like Java, you might see a try finally instead. So anytime you try to exit from your try block, it'll run the finally block first, and you'd have your exit code inside of there. Okay, so anyway, in this case, if B is already taken, I say lock, maybe I should say acquire, but it's too late. If B has already been taken, then we have a few choices. We could say release A, right? That would be no hold and wait. But what would that mean? Like, okay, so if we can't get B, then we just unlock A, and then what? This looks complicated. Maybe we'll come back to that. Similarly, we're trying to lock B, and we're just waiting. Someone else comes and takes lock A from us. That would also be what would this thread do when lock A somehow gets unlocked for it? A little tricky to figure out what's going on with the code there. Well, maybe we'll look at one or two solutions later. All right, so no preemption. Once a thread holds on lock, no other thread can take it. Still, this is not sufficient for deadlock. There's one more thing. Does anyone remember, if you've seen this before, do you remember what the last criterion is for deadlock? kind of a tricky one to define. It's called circular dependency. So I don't know how to write that this short, but we have one example here. This philosopher depends on, let's see. So after the first round, everyone has taken their left one. This philosopher wants this guy's stick. This one wants that stick. This one wants that stick, and so on all the way around. And in the end, no one can get one. In the A and B case, one example would be like this. Thread 1 says lock A, then lock B. And thread 2 says lock B, then lock A. So you sort of have this dependency between locks. Here, the release of A depends on being able to acquire B. Here, the release of B depends on being able to acquire A. And so that forms a circle. And if you have all these four criteria, then usually it's over. It won't take long before you have a deadlock. You might still have to get a little unlucky, right, with the timing, but after a while it's gonna happen. So how do we fix this problem for the philosophers? And then we'll talk about other programs. Oops. We don't want a deadlock anymore, so we have to change something in the system. Yeah. Take both at once. Yeah, that would be nice if you could do that. But we have one instruction at a time, so to speak. I guess the philosophers are not ambidextrous. But yeah, that's a good idea. So one way you could do it then, I suppose, would be to sacrifice 3 of these sticks and put a pair of sticks in the middle. And that sort of gets that, where you kind of get a pair of sticks at once. Any other ideas? Well, actually, we can sort of follow this. This one we can't do much about. This is just in the nature of sticks. Yeah.
I mean, as soon as one grabs one stick, you can lock everyone out until he grabs the second, and let everyone start grabbing sticks again.
Oh, okay. It might be a little hard to coordinate that, but I guess if everyone's like keeping a good eye on what's happening.
It could work, but
Yeah. So that seems almost like a central lock. I see. It's a little bit like the reader-writer lock that we talked about last time, or the one with the weight lock, where you have one lock in the middle that you don't hold so long. You only hold it until you have your 2 sticks, and then you release it. Yep. That would work. Another way to put that, I think, is to say we have a central coordinator. So there's someone in the middle, or one of these guys basically decides who gets to eat next. So your solution with a central lock, in that case, when you grab the lock, you become the coordinator. And in this case, well, you always decide on that you eat, right? But basically, that central lock is coordinating the rest of the work. That would work. Or you could always just have one philosopher say who gets to eat. And if everyone pays attention, that would also work. Any other ideas? Well, I propose we could break this one. We just allow philosophers to take sticks from each other. Right? In this case, it works, kind of. They probably get to eat a little bit, and then maybe a fight breaks out, and maybe it's not so good. What about this hold and wait? Can we break that one instead? It's enough. We have to have all these 4 criteria. So if we just kill one of them, then we're in okay shape. It's not a bad solution that you have, but there is one bit of a problem with it. So this is only 5 philosophers here, but imagine you have 5,000 philosophers. Now it's very hard to keep an eye on it if you want to do it your way, like grab 2. That's never going to work. But with a central lock, then now they're all fighting for that lock. So at some point it doesn't scale anymore. So the point of having many sticks is that many can eat. All right, so how about I take a lock, I take a stick on the left, and then if the stick on the right isn't available, I put down the stick on the left. And then I try again after a while. Yeah.
As long as you don't pick up the stick on the left until you have the stick on the right now, you can only try on the other opposite stick.
Oh.
Because if you put the stick down on the left, then you don't want to immediately pick it back up the next time you go to try.
Why not?
Because if every philosopher just sits there putting the one down on the left, picking up the one on the left, up, down, up, down, up, down.
Aha, okay, yeah. So we end up with everyone picking up a stick, they look at to the right, there's nothing there, and they put it back down. And then they take it up again. And so you propose, and instead they should go, take that one up, put it down, and then take this one up, look, and put that down.
Yeah.
They're still starving. It would look better. Yeah. Anyone know what that's called? So in this case, they don't get to eat, even though there's no deadlock. A deadlock means they're not doing anything, they're just waiting. Right? It's called a live lock. So a sort of a common live lock that we encounter on a day-to-day basis is when you meet in a corridor, let's say, and you go like that, right? If you weren't people and you were a little different, if you were perfect machines like these philosophers, you would have the same policy and you would just stay there, right? So yeah, you have to be a little more careful. So I suppose if we wanted to do it this way, we could add some randomness, right? And then probably on average this would work out. Like you wait a random amount of time before you pick up the stick again, right? And then probably people would be okay. Yeah. So that's generally the case for live lock. I think you usually get it when there's this perfect synchronization and everyone's the same. You can end up in trouble. But this is one way. Unfortunately, how long should that random waiting period be? It's hard to tune it to get it right. You probably end up with poor performance in the end. Or you risk actually having deadlock still. It's kind of or at least having a live lock that keeps happening. It doesn't seem like a perfect solution, but it seems like probably that would be somewhat okay. All right. We could, of course, just add another stick. If we add one more stick, in this scenario, we're actually okay. Because then one of these, so we add 2 sticks here. And one of them, I don't know who it is, but one of these 2 would get to eat, always. And then when he's done eating, then the next one will eat, and so on. And so that solves the problem. But this doesn't seem like a very general solution, because you can't just add another lock into your software. Right. Okay, and maybe that's a way to break the circular dependency. Right? Yeah, it is. If you put another lock here, then this one doesn't depend on that one anymore. He's got his own stick. So that's pretty nice. Some other way is there some other way we can break the circular dependency here?
One of the professor requests for a stick from his neighbor with a promise that I'll give it back to you for I'm done.
So that would be preemption, I think. Except maybe without the fighting. Right? You're polite about it. Yeah.
So the other proposal will go that I'm going to receive the stick as soon as he is done. So when it's still, it's not an infinite wait. He knows he's going to get back in some time.
Yeah. Do they all do it at the same time?
Whoever requests first, I mean, it's going to be only one request. The entire scheme of things.
All of them will be requesting, right? They all act the same way.
So the entire system will have just one request. So whoever gets that request first, and then that one is served.
Where does this request come from?
That would have to be working.
You have another lock for the request instead. Yeah, maybe.
No one of that box.
But then another alternative is that all of them make this request to their neighbor on the right. Then of course they all get the other stick and it's over. So yeah, I mean, yes, we can come up with sort of special situations that may apply for philosophers. But if they all sort of act the same way, follow the same rules, that seems difficult. So actually there's a standard solution for this that is really easy and that is highly recommended for every lock out there, every locking system out there, and that is to essentially number your locks, number your sticks. So let me put some numbers on it. And now instead of taking the stick on your left, you always grab the lower numbered stick first. Actually, let's back up a little bit. So we could say, oh, just take a random stick. Instead of taking the one on the left always, take a random stick. Right, then probably something's gonna work out. Right? But once let's see, that's once every 32 times, right? You might end up with everyone grabbing the stick on the left, and then it's over again. So the randomness doesn't really work out. But if we more strictly decide in which order you pick these sticks, and still follow the same rules, then we might have a shot at this. So here we say every philosopher grabs the lower numbered stick first, and then the other stick. So this one picks that one. Actually, now I need to draw to keep an eye on this. This one picks that one. Oop. Right. And now this one looks the other direction. And that's already taken, so he's going to have to wait. But that means that now philosopher 4, this philosopher can pick up the stick on the left as well and gets to eat. So this is a way to break the circular dependency. How do we translate this into locks? A ref counter? Nope. A lock will only ever have a ref count of 1, or 0 or 1. Well, you can have lots of pointers to locks, but
Just have pointers to locks, but then always grab the lower end. So the pointers, if they're stored in an actual array where the locks are.
mm-hmm. Or, well, that's the same as an address, I suppose. So you can acquire locks in order of their address, is what you're saying. So let's look at the code here. How does that translate for this one?
So you're just have like an array of locks.
Yeah, but we know the address of A and B. Say, so now,
But what I'm saying though is like in the boss, for example, you wouldn't be guaranteed the compiler puts things in the right order all the time, right? Or for A, B.
well, so this is very similar to what the philosophers are doing. It's just that they're not adding here, they're eating, right? And they're not doing anything in this part. So the compiler can't do anything for us. We've already told the compiler, lock A and then lock B. It's a little difficult with the addresses, right? Because the programmer doesn't know the addresses of the locks.
If they put an ampersand in front of it, they can just.
Yeah, but when you write the code, like, so how would you do that? So you would say like,
You say like if ampersand A is less than ampersand B, lock A.
yeah, and otherwise you would have two copies of the code. There's an easier way. Yeah.
You can have priorities of the locks, and then can grab the lock that is lower priority first.
Yeah, and how do we decide on the priority? So he's prioritizing based on the address, basically. The address is a little difficult because it can change, and so a programmer doesn't necessarily know it. At runtime, the program knows, so the programmer can make use of that, but you don't really know what the address is when you write the code. So you'd have to have if statements like that. Yeah, it'd be nice if you had some other solution where you don't have to know the address of the objects. But yeah, priorities of in some way, yeah, that's good. But how do we prioritize them? How do we decide which one to lock first?
Use the name of the lock.
That's right. In fact, it doesn't matter. You can use the lock that was declared first in your list of locks, or you can use the name of the lock, or you can use a hash of the name of the lock, whatever you would like. The third character of the lock, it doesn't matter. As long as you have an order, a strict ordering of locks, then that's fine. It doesn't matter in this case. If we switch out the 2 and a 4 like this, it'll still work fine. I mean, it won't be the same. This one will go like that. What else? Yeah, I don't know. But anyway, it'll still work. No matter which order we have, we don't have a circular dependency anymore because there's a strict prioritization of the locks. So basically what you want to do is make sure you always acquire your locks in the same order. You could do it by alphabet if you want, or you could just, at the top of your code, you put a comment, you say, these are the locks, you may only acquire them in this order. You don't have to acquire all of them. Like, if you have A, B, C, you can lock A and then C, forget about B, that's fine. But you cannot lock C and then A, because then you could end up with a circular dependency. So that's what people do. Right? You specify in which order locks are acquired, and if you don't, well, then you're going to have a deadlock. This gets pretty difficult because it's not always that you write all the code. Right? You might include some library in your code. So now you acquire a lock, and then the library acquires a lock. Probably that's fine if the library then releases the lock before it comes back to you. But if it holds on to it for a while, now it starts getting like you could still have circular dependencies. So yeah, usually you want your library functions to just release any locks before you come back, or you may well have some trouble. Okay, another way that we could do this. Let's see, we're done with this. Yeah, I think so. Yeah, so actually, while we're on the topic of deadlock, let's look at this in more of a kernel context. So here things get a little worse, because mainly, I suppose, because of interrupts. So you could imagine a function just acquires a lock, right? And then we have our interrupt handler that says lock A, what am I doing? Okay, that's much better. Right. So here we have just the one thread and just the one lock. Or I suppose it's a single core machine. We're just executing a system call or something. We acquire our lock A, and then a timer interrupt goes off, or any other interrupt, and the interrupt handler tries to lock A, and then it's over, because lock A is not available. So what happened? There's only one lock. Why do we have a how do we get a deadlock with just a one lock?
Interrupt went off after function locked it before it unlocked it.
Yeah, but we're not supposed to be able to get deadlocks if we don't have circular dependencies. How can we have a circular dependency with only the one lock? What's the dependency here?
So go to or function call, I guess.
The dependency is the CPU. Like someone came and took the CPU away. Right? So, and they're not giving the CPU. So the code, this code here holds A. And normally, in normal code, the CPU is not something we think about. It's abstracted away nicely by the OS. So we always have it. Like, we're guaranteed. Eventually, we will come back to my process. I get to run the CPU for a while. But in the OS, unfortunately, it's not like that. So now we hold A, and then an interrupt comes, and it, by default, holds the CPU. So now I depend on the CPU in order to unlock A. And the interrupt handler depends on A in order to unlock the CPU, to return the CPU, right? So we have a circular dependency with only the one lock. All right, how do we fix this?
Disable interrupts.
Disable interrupts. All right. That's what it says in the spin lock code in XV6. Someone's been doing his homework. Yeah, that's one very good way. If you just, before you acquire a lock, you disable interrupts, then we know that the CPU is ours, because interrupts are the only thing that can take the CPU away. Pretty good. Any problems with that? Let me put it this way. Linux does not disable interrupts unless it's really, really necessary, which it usually isn't.
I mean, I could see an issue happening in which there's a long running process and it's disabled interrupts, so then it's logged in that the interrupts are not disabled, but now it's just doing this for a long time and everyone else is waiting on this.
Yeah, so we're doing something over here, and it's long. And now for a long time we're not getting those interrupts. Interrupts generally happen because something important is going on. We're supposed to react to the interrupt. It could be the user is moving the mouse around, and so the mouse pointer should be moving on the screen. If we disable interrupts, then the mouse pointer won't move until we're done with whatever we were doing. If it was something somewhat long, what could it be? A large mem copy for whatever reason. It could take milliseconds to do a large mem copy, and now you'll see the mouse pointer is just all jerky, and it might not even move, so you might even lose some of the interrupts. Right? The user moved the mouse or the touchpad or whatnot, but the pointer never moved because we lost all those interrupts. It's a possibility. Of course, that's only if we do something long here, but oftentimes, whatever the interrupt is saying is more important than what we're doing now. So we really ought to be handling that first, right? That's why we're getting interrupted, because this is more important. So we're sacrificing performance. Potentially, we're sacrificing correctness by losing interrupts. That's how XV6 does it, because it's really simple. So usually that's how XV6 does everything. Okay. Any other ideas?
Can we make the interrupt release all the locks before trying to acquire them?
Ooh, let's see. So you're saying, actually I'm not sure what you're saying. So the interrupt would release the lock while we're inside the critical section here. The interrupt would just say unlock A.
Yes, basically the problem is that since F has logged A
Mhm.
and the interrupt has occurred and the interrupt wants A but it hasn't been released, so why don't we make an instruction that can release all the locks before trying to acquire anything like within the interrupt?
Well, I can propose an even easier way then. Just forget about locking A. It's already locked. So what happens if we don't acquire A?
Can anything else come in between an interrupt? Is it possible?
No. Well, I mean, yes, another interrupt, but let's forget about that for now. One can also set it up so that when an interrupt happens, interrupts are disabled after. Like the CPU has an option for that, at least the x86, I think. But we don't need to worry about that right now. We have bigger concerns. So we were in the middle of doing something here. And then the interrupt comes. So it's not that the interrupt operation will be disrupted, although that's possible too. But whatever we were doing here might be lost. So let's see. I actually can go both ways. So we read some value and we add it in a register. And then, interrupt goes off. And here we do read the same old value now. We hadn't yet written it back. Right? And so, yeah, we lose correctness.
What if we check if the lock is locked and then exit?
Okay, we use a try lock instead. So we say, sorry, someone else holding the lock, let's ignore this interrupt.
But that would be a problem for user experience, right?
Well, it could be that now we get the same thing with the mouse pointer, that we just don't do anything. But you're kind of, I think you're sort of on the right track. But we have to do something more here. Yeah.
You delay the interrupt until after the unlock and
Like a sleep mode.
yeah.
So the delay is essentially what happens when you disable interrupts in hardware. Like if you turn it back on, they come in rapid succession. But there's a limited queue. But okay, so we can't really delay the lock. Well, we can delay the handling maybe of the interrupt. Right? So we say, mouse pointer event. Let me put it in this queue. And then when things calm down, I will handle it. Yeah. If you've been looking at all at the Linux code, there's something called what's it called? A top and a bottom. Let's see, top half and a bottom half. So there the idea is the interrupt handler does not acquire any locks that are ever acquired in other code. So the rule is whenever an interrupt goes off, you cannot acquire locks that could potentially be held already. So top half does not acquire normal locks, or it's called only interrupt context locks. So it could be that you have multiple cores running, they're all in an interrupt handler, and you may want to coordinate between those cores. So you have locks that are only ever acquired when you're handling an interrupt. And so that can be okay, deadlock wise, but it's not okay to try to acquire a lock that could potentially be held already by the normal processing. And then we have a bottom half. This is executed in process context. I think it's called process context. So here, this is during a normal system call, right? The system calls don't happen at random, just anywhere, any time. So those are different. It's the hardware interrupts that come in at arbitrary moments. Those make life hard. So now we basically put in the top half, we just put in a queue saying this is work that needs to be done. If any, in order to do this work, if we need to acquire one of these sensitive locks, if we need to acquire A here, then we go like this. It'll be called BH, and then actually I'll say like this. Okay, so this is a sort of a standard design in the Linux kernel, where the hardware interrupt makes this happen. It just puts it in a queue. And then we have somewhere else in system call handling, or sometimes even running a separate kernel thread, or maybe in the scheduler, somewhere we have a little call that says, oh, let's check our queue. Is there anything we need to do? And in the queue is a bunch of these. Right? So now we run those bottom halves. And because we're in process context, this is not at some random point. This is exactly where it's safe to try to acquire locks. We know that these locks are not held at the moment. Then we can perform our operations. So then we avoid having a deadlock. Another solution is to have, well, if we kind of realize, actually let's, before we go to the interrupt thing, let's look at another potential deadlock. So it goes so here we have the same developer probably writing two different things, two different functions. Sort of independently. So this is our function that allocates a new process. No, this is fork. Right? And fork needs to have access to the p table. So we acquire the p table, right? And then this is allocproc. Allocproc needs to access the p table, so we acquire the p table again. The p table lock. Right? And now it so happens that fork needs to call proc-alloc, or allocproc. Maybe there's some other places that call allocproc as well, so it just makes sense to acquire the p table again over here. So of course this is a deadlock, but only, actually it doesn't cause a deadlock on xv6. Has anyone seen what happens on xv6?
I think people panics.
Yeah, there's a panic. It says held, I think.
Yeah.
Right? So it says, oh, I tried to. So normally when you have two threads trying to acquire the same lock, normally one would wait for the other one and just run. Right? It's not that, oh, the lock is already held, so I will panic. That's not how locking works. Right? But if the same thread tries to acquire the lock, I hold it here and then I acquire it again, well, then we panic. How do we even do that? How do we know that we're holding it?
The lock can have a reference to the current thread.
Yeah, the lock could have a reference to the current thread. It's not, in the OS context, that's not quite good enough, because you could imagine the OS switching processes and holding the lock between switching, right? So that's not the granularity. The granularity is the core. We need to know which core is holding the lock, right? It's okay for one core to hold the lock and another one to try to get it, but it's not okay for the same core to try to get the lock that it already has. So that actually, I think, is what's going on. Let's take a look at held. Come on. Oh, that's not what it says.
It's something else. It should be in spell.
Yeah, should be close. Sleep lock, spin lock. Okay, it must be here somewhere. Yeah.
It's holding.
Oh, it says panic acquire. Okay, good. So if holding lock, and what does this holding do? Is it hiding up here somewhere? Well, anyway, here it is. So whenever you acquire the lock, we say which CPU is holding it. So this is, it says for debugging, and that's actually true. It's only necessary for debugging. This panic stuff is not something that the user really desires. Right? If we have bug-free code, we will never have a panic anyway. So, but it's really quite useful because now we can tell that we tried to acquire the lock again. But there's other ways to handle this. Like, why do we even care? If we're holding the lock, why not just go on? The lock is ours. This is called a re-entrant lock. Right? It's actually part of the POSIX mutex standard. You can specify this is a re-entrant lock versus a non-re-entrant lock. The default, I think, is that it's not re-entrant. Oh, there used to be a nice little comment here. It said XV6 does not support re-entrant locks. It's not there anymore, but it's still true. We can see it here, right? That makes it not support re-entrant locks. So, yeah, why do we care? It's actually two sort of contexts here where we maybe let's see. Yeah, this cannot happen for an interrupt. Right? We can never get an acquire in an interrupt because we disabled the interrupts first. So whenever you try to acquire a lock, there cannot be any more interrupts. So we would not be holding it. So that's not it. It's really for normal thread context or process context locks or lock acquisitions. This is a really hard nut to crack. Let's look back at this. And I highly recommend that you never use re-entrant locks. But they are supported by POSIX. The pthreads library must include re-entrant locks. So, they're convenient, right? Because now you can write code. You don't have to write code like, let's see, this wait one. Oh, wake up one. Look at this. Wake up acquires the lock and then calls wake up one. Wake up one does not acquire any lock. The only reason that we do all this nonsense is that we don't have re-entrant locks. Right? So now, if you already hold the p-table lock somewhere else, you must call wake up one, otherwise you get this panic. So if we just enable re-entrant locks, well, then we don't have to have all this stuff, and it would just be nicer code, right? So the problem is, man, what is this? Sharp pieces. Anyway, the problem here is when you write a function like this one, you assume that the p-table, let's say we wrote this function with acquire wrapping it inside of here. When you write it, you assume that this process table is in a consistent state. Right? Everything is fine. If you're if you make you have a search function for a linked list, right? You assume that you will be able to traverse the linked list while you're holding the lock. This is the whole point. It's atomic inside of the acquire and release. Of course, the lock is held, so we should be okay. But there's one more thing going on. If you're being called by a function that's holding the lock, they already started modifying this shared data structure. So you could imagine something that goes, let's see. I need to have a good example of this one. Okay, so here. Linked list, add, no, move, let's say. So we acquire the lock. I'll say lock, that's easier. Linked, come on, linked list lock. Okay, unlock linked list lock. So here we go. Remove element from lock, from list, and then maybe clean up list. I don't know, it's a special list here. So when you remove something, there's some dangling pointers, and then you do a little cleanup operation, and then the list is fine again. But we removed it, and this is a move, so now we say a little insert modified element. Actually, let's just do like this. Ah, this is better. All right, so we remove element 1 from list, and then we insert element 2. Go L remove. Okay. Clean up list from L1 removal. Right. So normally, when you do a remove, it should be like that. But then we happen to do the insert inside here, between the two. So after the remove, the linked list is not quite in a good state. But that's okay, right? We're in a critical section here. No one's going to mess with our list, so that's fine. Except inside of this LL insert, it says traverse list. Oh. Right. So now we call LL insert, and we start traversing the list, but the list is all broken. That should not be possible because we're trying to acquire the lock. Whenever we acquire a lock, we have an atomic access to this lock, and it's always in a consistent state when we get when we enter a critical section. So there isn't really a race condition. It's sort of like, I don't know, it's a static race condition, I suppose. Race conditions usually happen by timing, but here it's just by the interleaving of the actual operations in the code and the sequential operations in the code. So you get this problem because we assume whenever we acquire the lock that the list will be in a consistent state. And that's not the case in this situation. So by disabling these reentrant locks, now this won't even work. Right? Actually, it will compile. At least in C, it will compile. But then the first time we try to run it, we get a panic, and we know to fix it. Right? And then if you call this insert 1, well, then you know you have to be a little more careful, right? There's something special about this. So it's one way to kind of help the programmer. Yeah. So sometimes you want to be a little more explicit about this. The same is true for the interrupts. It's worse for interrupts. It's not like we can enable our interrupts and you then go with reentrant locks, because now wherever we are inside of any lock, it can just get preempted. We start running interrupt handling code instead. Is clear? Any questions on interrupts and deadlock before we move on? Some of my colleagues have started experimenting with peer instruction. I'm not going to do that this semester, don't worry. But I'm curious. So there the idea is you pose some questions along the way, and then you say discuss. And then people discuss between themselves. And according to all sorts of studies, you learn much better, because professors have been doing this for way too long, and we don't know what's hard to learn. Whereas if you talk to each other, you kind of have the same context, and it's easier to explain to each other than it is for me to explain to you, because I don't know what's hard. I think it's an interesting concept. Apparently it's quite successful, at least in other fields. In CS it's relatively fresh. I think if you take a class with Cynthia Taylor, or with Joe Hummel, or with Chris Kanish, you'll run into peer instruction with clickers. Yeah, at some point maybe I'll try it. All right, so that said, do we kind of know how to avoid deadlocks? The easiest way is to just use one lock. Like whatever program you have, just the one lock. That'll do. And the other way, of course, is to order the lock acquisitions. Actually, that kind of works out if you have libraries that you call, and those libraries never try to acquire your locks. Like you're never passing in a lock that they will acquire. Then you have an implicit ordering. You have one lock, and you call some library and they use some lock internally. Well, you're going to be acquiring your lock first, and then inside of their function they'll acquire their lock and then release it. So now you have this implicit order. That works. This is also why we don't worry about the user programs acquiring locks and the kernel acquiring locks. The kernel has a lot of different locks, and user programs can do whatever they want. They will never hang the kernel, because the kernel doesn't try to acquire user locks. The user doesn't try to acquire kernel locks either, but that's forbidden. The kernel can, of course, acquire a user lock, but it'll never try, because that would be very unsafe. Okay, we have a few more minutes. I thought we'd take a look at conditional variables. Maybe not. There's a couple more pieces we need here first. So there are a couple of interesting other phenomena that have to do with locks. One is starvation. So with, how can I make this a little better? All right. So starvation doesn't happen sort of theoretically with the locks we've been talking about, but you've seen the implementation of our locks, and in a bad implementation you can easily have starvation. So if you think about a spin lock, it just tries to acquire the lock, gets it, does some work, releases it, and then maybe it goes right back to trying to acquire the lock. If your CPU is being very greedy, it might say, oh, I just released this lock, we're trying to acquire it again. The fastest would be if I take it again. All right? Whichever CPU has the lock at the moment, or just had the lock, is the one that's the closest to the lock. So to get maximum throughput, we should acquire it again on the same core. Right? So if you now have a program or one thread that really wants to see this lock a lot, it might end up always getting the lock. No other thread ever gets it, and they all starve. Prioritization often caused by prioritization. Ooh. So I think the countermeasure to that, well, there's a couple of things going on. In the Intel CPUs, they do this reacquisition of locks. If there isn't a whole lot of work between, it'll come back to the same core. But I don't know how they do it, but somehow, after a little while, the lock will go somewhere else. Maybe there's a timeout, or maybe it's possible that it even waits until the timer interrupt goes off. I haven't looked into it. But there's some mechanism that prevents complete starvation just in the CPU. Another way to do it is use a ticket lock. Right? If you're able to get a number, and that number thing is not contended, right? Everyone's waiting for the number on the wall to go up, but the piece of paper, usually there isn't a whole lot of people there, so you can always get a piece of paper. So ticket locks prevent it. But imagine a new policy where we're trying to minimize latency. With ticket locks, you get long latency, because whoever waited the longest is gonna get served next. So so maybe the max latency is smaller, but on average, it's always everyone who comes there is upset. Right? They're all been waiting forever. Right? So now, if you want to have only happy customers, then you will serve whoever came last. Right? They have the highest number, they get served first. Everyone you talk to is really pleased because they got service right away. That's great. Sometimes that's actually better. But in that case, whoever came in first will never get served. If the store is always busy, they never get served. So then that's another way of starvation. A LIFO policy, last in first out policy, also causes starvation. Okay, so generally this is something one needs to look out for. Right? In locks and generally in sort of scheduling policies. So let's think about our scheduler for a moment. We've talked about prioritization before, like we might have high priority processes, low priority processes, and even within one process we could have high priority, low priority threads. So if we execute always the high priority process first, we might end up with starving a low priority process. That seems pretty obvious. So we had some, at least in the completely fair scheduler, we had this idea that a high priority process should get a larger fraction of the CPU, but not the entire thing, because then you have starvation and that can cause all sorts of problems. But in other situations, maybe it's actually a really important process. So this happened in what was it called now? The Mars,
Curiosity.
not Curiosity. It was the one before. Let's see, Mars rover. Mars Pathfinder, it's called. And so this is actually this is a very short write-up of it. Yeah, I recommend you take a look at this. Search for Mars Pathfinder priority inversion. So the general idea here is a low priority thread acquires a lock. And in comes a high priority thread. Now, the low priority thread hasn't finished yet. So it's not going to get the CPU again because the high priority thread is running. Now the high priority thread wants the same lock. So now, unfortunately, the high priority thread essentially has low priority because it's waiting for the low priority thread to release the lock. This got a little more complicated than that in the Mars Pathfinder. But basically, that's what happened. It started rebooting over and over because it wasn't able to, whatever it was, clean up do some garbage collection or something. I don't remember what the issue was. But basically, with priority inversion, you have high priority threads that inherit the low priority of a lock holder. So the solution for this, priority inversion, high priority thread gets low priority due to locks. So the solution for this, can anyone propose a solution? So now the high priority thread is just sitting there waiting for the lock. But it's spinning, because this is an important one. It's not going to go away. What's that?
A sleep lock.
Yeah, it'd be nice if it did a sleep lock. But this is, let's see. Yeah, in this simple case, I think that would work fine. Well, let's say we don't have sleep locks for now. In the 3-thread case for this Mars Pathfinder, it doesn't work. But I can't put my finger on why now. Yeah.
Set the low priority thread to high while it's waiting.
Exactly. So now a high priority thread is waiting for this other guy. We can't just throw the guy out of the queue. They already started working on the data structure. That's no good. It's not safe to stop them running, but we at least hurry them up. Like someone really important is waiting for you, just get it done, right? So the priority inheritance solves the problem. So this is not strictly an OS or even just a systems problem. This is all over the place. This will happen in a grocery store. Right? You don't just interrupt the transaction. Maybe you let someone pass some people in the queue, but whoever's at the register, you don't just throw them out because the king arrives. Like, you just hurry them on. So, yeah, priority inheritance will take care of that. The manager probably goes to the cash register and takes care of it. Make sure it happens quickly. Right. Okay, so we're going to have to talk about condition variables next time. And actually, did we have any questions on the homework? I forgot to ask about that. No one came to office hours yesterday. What's up with that? We have the hardest homework yet.
Was it you that said normally don't go to office hours the day of the homework is due? Or?
The day of, yeah, but that's today.
Do you not have the office hours on?
I have Tuesday and Wednesday office hours. And Nilanjana says no one's coming to office. Very few people are coming to office hours in general. So anyway, there's more chances. We've extended it until till next Thursday. Were there any questions for now? Yeah.
So it's something about if you turn in for today, does it really have any bonus?
Not a bonus. You get a bonus problem. So I'll figure out something. So you're done with it?
Yeah.
Cool. I'll figure out another thing for you to do. Unless you already have a solid A, in which case you maybe don't want it. That's right. Okay. So yeah, do come to office hours. I think Nilanjana will announce some hours or some sort of workshop. Get this homework out of the way. Okay. Have a good weekend. I'll see you on Tuesday.